All right, I've got 10 o'clock. I want to welcome everybody to our first implementation webinar for 2025. So this is our From Research to Implementation webinar series. And we really like to take topics that are out there that NCAT has had something to do with and somebody has been using in the field that we think that others can gain information from or gain knowledge and then use in their jurisdiction or in their company. So today's topic is production testing for BMD. BMD is such a hot topic. There's so many agencies around the nation that are going towards BMD. There's so many contractors who are exploring to try to figure out where their mixes are, how they're going to be able to work with their state as their state moves into those different production stuff. So our folks that we have today, as always, we've got Nathan Moore here. He's the Assistant Director for Test Track Research at the National Center for Asphalt Technology. He's responsible for overseeing all the test track programs. Prior to that role, Nathan served in the laboratory as one of our research engineers for 8 years. He specialized in BMD there and friction pavements as well. He holds a bachelor's degree and a master's degree from Auburn University. And he's also a licensed engineer in the state of Alabama. And he is a licensed blanket fort builder for his children as long as his wife is out of town. So Adam Taylor is also with us today. He is a research engineer here at NCAT. He started his undergraduate co-op back in 2003, and he's been an engineer with NCAT here since 2008. He specializes in mixed performance testing of hot mix materials. He's been involved with multiple NCAT projects related to BMD. He runs a lot of our round robin stuff that if those of you have been involved in that, he's the one that does a lot of that work as well. He's definitely an Auburn University graduate, and he's licensed in the state of Alabama, and he enjoys heavy metal concerts. I know that too. So Joe, let me make sure. Schroer, is that correct, Joe? Okay.
Great.
He's a licensed professional engineer in Missouri. He retired after 30 years of service with the Missouri DOT. He's been a part of the contracting industry for the last 12 years. His duties with NB West Contracting include the oversight of their quality control and mix design development, as well as the investigations of new products and specifications. And that's just a tremendous amount of experience that we have with Joe, and we're very grateful that he's here. So I do want to remind you a few things. Please stay muted while you're with us here. If you have a question, I'm going to put up the chat box. Please put your questions in the chat box. We'll round those up towards the end, and we'll go from there. Nathan, take it away.
Well, good morning, everybody. So many of you guys have participated in these webinars, so you sort of know the format by now. But for those of you who don't, we're going to go over I'm going to go over a very brief introduction about the topic and extremely brief overview in NCAT's history doing this. But then I'm going to turn it over to Adam Taylor to do a deep dive into NCAT's work in balance mix design testing during mix production. And then we're going to hand it over to Joe for the industry perspective. And, Joe's been doing this for quite a long time, and he'll talk more about that. And then when we're done, we'll close out and we'll have some time for questions. Please put those questions in the chat as we're going. Feel free to go ahead and type them in, and we will answer them at the end. And then we'll close out. So NCAT really started kind of BMD style testing back in 2015, although we weren't really calling it that at the time. That was part of our cracking group experiment where we were looking at a lot of these BMD tests. We sort of officially started BMD during production on the 2018 test track. Adam and some other folks at Fanyin and some other folks at NCAT wrote a report on this. It's NCAT report 20-02. Where it's the performance testing for quality control and acceptance of balanced mix design. And that was kind of our first dipping our toe in the water of what does BMD look like on during production when you've got tight schedules and uncertainty about mix quality and things like that. So in 2018, we started with just 5 mixes. Learned a lot of lessons. Adam and I were in the lab at the time, did a lot of work in trying to improve all kinds of things. Adam's going to talk a lot about specimen preparation and data quality and stuff like that. In 2021, we tested 14 of the test track mixes during production, and so we had quite a big database looking at all kinds of mixes. Just about any surface mix that went on the track, we sampled, with the exception of the open graded mixes. And then in 2024, Adam and his team, they tested 16 mixes, so it's growing. It's a tremendous asset for me as I was kind of overseeing the track build to have Adam and his team testing testing mix quality and having rapid results to know not just did we hit traditional quality control measurements like gradation and asphalt content, but to know that we were on track with some of our performance numbers. So we've learned a lot of lessons over the years. Again, this is something very near and dear to my heart because before I took over at the test track, Adam and I were kind of two peas in a pod related to balanced mix design and specimen preparation. We wrote a guide for Napa on BMD performance testing specimen preparation, which is really important. But we've learned all kinds of things about sampling, and we could talk for hours about specimen preparation. Testing efficiencies, little ways to make up time here and there to shrink it as short as possible. Adam is incredible at data reporting and data analysis. He's got a really organized mind, and it's really helpful. And all this is important as you move forward to benchmarking, which is something that as a state is getting interested in BMD, that's really important. I don't want to take too much of Adam's thunder, though, so I'm going to just go ahead and turn it over to Adam and let him discuss NCAT's recent experience with BMD testing during production.
All right, good morning, everybody. I'm going to talk to y'all a little bit today about our BMD testing efforts in support of the 2024 test track, or the test track build. So this all happened in the fall of last year. See if I can advance my slide. So you're right before the 2024 track, as Nathan said, he worked in the lab with me for a long time, but he moved out to the test track as our assistant director, and we had two new hires come into the laboratory, Graham Hurley and Zane Hartzog, both PEs, both with a decade plus of asphalt experience. And we couldn't have done this without them. So all three of us were critical in getting this effort done, and these guys have been, I can't say enough about them. They're amazing. They did amazing work on this effort. So what we did this time was we wanted to do BMD testing in support of the 2024 test track reconstruction. We tested 16 total mixes. Each one represents a test section on our test track. These were a very wide range of materials, different binder grades, different wrap contents, additives. So there were some plastic additives, there were some rubberized additives, rejuvenators, etc. So you want to pull the lever on the mix randomizer, and out would pop a lot of the stuff that ended up on our test track in this cycle. So it wasn't necessarily a lot of vanilla mixes. There were a lot of unique and challenging mixes as well. Our objective was to conduct BMD testing in support of construction. Our scope of work was the ideal CT and the high temperature IDT, because that is a rapid cracking test and that is a rapid rutting test for BMD that can be turned around the same day if needs be. We also ended up testing a good bit of Hamburgs as well, or having the specimens to test Hamburgs as well in support of construction. But our main goal was the CT and the HT test. We tested over 100 ideal CT specimens. Our average coefficient of variation per set was 17%, which is on par with our historic estimates that range from 15 to 20%. We had two mixes with CTs over 200, but they were both SMAs. Generally speaking, SMAs give extremely high CT index values and extremely low high temp IDT values. Our average dense graded CT range from 33 all the way up to 150. So we have a wide range of materials on the test track. It'll be interesting to see how they perform coming into trafficking of this 2024 test track cycle. For the high temp IDT, which is our rapid rutting test conducted at 50C, we tested 62 specimens. That is a more repeatable test. So generally, that was an average coefficient of variation at 8.1%. And again, we got a wide range. We've got very soft to stiff. We have materials ranging from 16 PSI all the way up to 44. Now, the ALDOT design value for this test is 20 PSI, but we all have kind of had a feeling like, is that really like as low as you can go? Can you go lower and still be okay? And that's what the 2024 test track is going to tell us. We have a couple of mixes out there that are below 20 PSI on a high temp IDT. How will these mixes perform as they get trafficked? You know, can we push that design threshold a little bit lower and get more cracking resistance and still be safe on the rutting side? It'll be very interesting to see as that moves forward. Just kind of as note keeping, I didn't put it on here. Our goal was to test 6 specimens per set for CT and a minimum 3, but we usually tested 4 specimens per set for high temperature IDT. So generally our goal was to make 10 test specimens that would be tested for CT and for HT. So just a quick note about kind of our operations. There were 2 sort of parallel track QC activities going on during the test track build. There is a lab out at the test track that is used entirely for QC during the build, and that's what you'd call your run-of-the-mill QC testing. That's your in-design pills, that's your rices, ignition AC contents, gradation. This is information that's being fed to Nathan so that he can make a call on whether or not the section is of sufficient quality or has met our targets. On the parallel track, we get a sample of mix at the sample stand at the test track, and we bring it back to the NCAT main lab. We bring it back here because our testing equipment's here. There's space to work. You know, we're not conflicting with each other out at the test track for the same space and ovens and factors and whatnot. So we get generally sampled 2 buckets of mix. We load it up in the back of a covered pickup truck with this really high dollar insulation material wrapped around this buckets here with a sophisticated weighting system on top there. And we bring it back to the NCAT main lab. It's about a 25-minute drive. We always check the temperature of the buckets when they get here. More often than not, they're going to be at compaction temperature or very near to it. So for BMD production testing, generally we're going to sample 2 buckets of material. We really need 1.5 at most, but we want to make sure we get enough so that we're not scraping the bottom of a segregated pan to get our final samples that go in for testing. You always want to sample more than you need. I'd always much rather throw away material than run out of material. The quartermaster, which you see here, is sort of our standard operating procedure for helping homogenize the buckets. So we get 2 buckets out of the back of the truck, we bring them back to the lab, unload them, we put them through the quartermaster, and those 2 sample buckets become 4 blended buckets. This is just to help homogenize the material. So that helps, if there was any segregation in the sample, that helps blend it through. This is covered in AASHTO R47. This is mechanical splitter type A. So we would then take these 4 blended buckets, we put 3 back in the oven with a lid on, and we're going to take one of these buckets and proceed directly to splitting out samples. So from that first bucket, we're really just trying to get our trial weight nailed down. We would split out 2 rices. Now, running the rices is the critical path in a production test. You need the GMM to know what your air voids are, and the rice is the longest test. A rice takes a lot longer than a bulk. It takes 15 minutes under a vacuum, and then it takes 10 minutes per bowl or flask underwater. So that's your critical path. So we're trying to get these split out, spread out, cooled, broken up, and testing as fast as we can. Usually one person is doing this while the rest of us are splitting out. We would always split out 2 ignition specimens. These were just a backup for Nathan in case there was any question about the AC content or the gradation for the materials at the track. And then we also split out 2 or 3 62 mil trial weight specimens. Now, in our case, we had not run these mixes through that plant before. So our starting trial weight was the trial weight we had used during the mix design. So if we had done a BMD design and we had made 62 mil specimens and 2,500 grams was our specimen weight during mix design, that would be our first trial weight for production. We would also probably make another 1 or 2 trial weight specimens just because you have time. like I said, the critical path is the rice. And you have time to make 2 or 3 trial weight specimens. You have time, you have material, and the worst case scenario is having a question about your trial weight and missing all your air voids later on. So it's better to just make a couple of extra trials up front because you have time, you have material, and the cost of being wrong is much higher. So that's generally our process. So we'll take that initial trial weight from design, and I'll usually do one plus or minus 20 grams from that, because more often than not, your production GMM is going to be a little bit different from your design GMM. It's just going to change a little bit as it goes through the plant. So you may be a little higher, you may be a little lower, and consequently, your trial weight is going to be a little higher or a little lower because of that. So you have to anticipate it's not going to be the exact trial weight that you got during design. Now, if you're doing production, at a contractor's lab and this mix has been run through the plant before and you have a trial weight from a previously run mix, that should be your starting trial weight because that's a weight that's gone through a plant before. So again, critical path, verify the GMM, verify the trial weight. So we compact these trial weight specimens while the rice is running. We are rapidly cooling them. So we've got them under 1 or 2 fans. And if you have one room that's colder than another, put them in that room. For whatever reason, our bulk lab is frigid and our mix lab is a sauna. So we generally take the specimens from our mix lab to our bulk lab to cool them off in there. Tools for efficiency. We refer to it as hot bulking. So on the trial weight specimens, we want to bulk these specimens as soon as we can. We want to cool them for as long as we can. And more often than not, they're still a little bit warm to the touch when we test bulk specific gravity. That's fine. We are just trying to verify what the weight that needs to go into the mold is before we make our main body of specimens. So once that specimen is cool enough to comfortably touch, we're going to go ahead and bulk it in a production setting because we need that number rapidly. So I've got 3-minute rice in quotations here. So this is a Nathanism, so let me explain it. So what we'll do is we'll get our rice running. It's going to spend the entire 15 minutes under a vacuum, and then you have the 10 minutes underwater for either each rice bowl or flask, depending on what method you're using. So you can see in the picture here in our bulk lab, we have a rice station in the middle and we have 2 bulk stations. What we do is we take one bowl, we put it in each of the bulk stations so they're running in parallel, not in series. And then we're taking that underwater weight at about 3 minutes and calculating the rice. Now, we still run the rice to the full 10 minutes underwater. We still get a final value. But what we've seen more often than not is that underwater weight at 3 minutes doesn't change a whole heck of a lot from what you eventually get at 10 minutes. So we use that if we're in a hurry, we'll use that 3-minute number to go ahead and calculate our air voids and our trial specimens, and then go ahead and make a call on what our weight in the mold should be for the rest of the samples for that mix. So it's a tool for speed. Having a couple of bulk stations helps, so you're not bottlenecked. Having 2 rice shakers side by side, so you're not running one rice at a time, that helps, so you're not bottlenecked there. So that helps us get that number as quickly as we can. Now, again, we leave the bowls in for the full 10 minutes. We report a final value, but that 3-minute value is just so we can make a call and move on as quickly as we can. So based on our trial weights and based on our bulks and based on our GMM, we're going to calculate our air voids, and then we're going to use our trial mix weight sheet to adjust our mass for the remainder of the specimens. At this point, I should have a mass that I feel comfortable with putting in the remainder of the specimens. At this point, we go into production mode. So we've got our number. I'll say, okay, we need 2,465 grams in the mold for this mix. At this point, we are trying to compact the rest of these samples as fast as we can. We have 3 blended buckets remaining. What we do is we'll split out one of those buckets into pans, put the pans in the oven, and then either myself and Graham or Zane, we're compacting these as fast as we can. And we generally have one person loading the compactor, one person unloading. That's how we got speed. So we were just trying to move these samples through as fast as we could. What we didn't want to do was split out all of these buckets and then have a bunch of small samples of mix in the oven for an extended period. Smaller volumes oxidize faster. So we didn't want to have a bunch of pans in the oven and then those pans be sitting in there for an hour or an hour and a half. We wanted to split these out, compact them as fast as we could. So generally our speed came from the fact that we had 2 people on the compactor. You know, one person loading, one person unloading. And then we would end up having generally 15 to 20 specimens at the end. And you see 1 section's worth on the table under the fan here. Let's see. So for our test track efforts, all of the specimens were compacted the same day as paving. So you'll hear them called production specimens or hot compacted specimens. This is reheated plant mix. It's the same terminology. Generally, BMD testing was conducted the next business day. Because of the paving schedule and because of the way logistics worked out at the track, sometimes they were paving these sections in the morning. Sometimes they were paving them as the sun went down. In order to not have the we're at the lab past midnight experience, we just made the call across the board. Like, hey, okay, we're going to make all the specimens the day of compaction or the day of paving, I'm sorry. And then we're going to test them all the next day. So across the board, you know, they were all tested on D+1 essentially. We averaged about 1 hour and 45 minutes from the time the bucket arrived at the lab to the time the last specimen was compacted and went on the table. So we kept a log of the time everything arrived, and we had the times from the height sheets from the compactor. That speed essentially came from, you know, trying to run rices in parallel on multiple stations, understanding critical paths, and then having 2 people working to compact these specimens as quickly as possible. And a lot of times that was necessary because we had several instances where we paved 2 sections back to back. For instance, like, you know, a control mix and then a mix with an additive. But Nathan would keep the plant hot and just pave the sections back to back and just make an adjustment at the plant. We had to be fast, or otherwise that second mix was going to arrive and we were already going to be behind the 8 ball. So for what we did, it was about a minimum 2-person job. But when we did a back-to-back pave, it was a 3-person job because we would have one of us go get the first sample, bring it to the lab, go back to the track, get the second sample, and then come back here. So just a couple of oddities, and then I'll finish up. So this is an example of where gradation matters. So I kind of mentioned a back-to-back pave, and we had one instance where we had an interesting like textbook example. So we paved an HMA and a WMA back-to-back one day. Now, generally, your trial weight can be calculated from the ratio of the GMM if the gradation stays the same. So in this case, we had our second mix GMM was slightly higher than the first mix, and that would lead to about 10-gram adjustment in our trial weight. Okay, more often than not, this works. But what we came to find out later was this mix didn't behave as expected. For our first mix, you know, that's the mix on the right here, the WMA. Most of our samples were within our tolerance of 7 ±0.5% air voids. And then we made a slight adjustment to the mass for the second mix, and our air voids cratered. Our average dropped down to the low end of the spec with about half our specimens missing air voids. And we were lucky to get enough to do our testing. We had just made so many that we were able to have enough redundancy to do the job. So the logical question is, what happened? So we ended up doing kind of a root cause on this. And for that second mix, you know, after some discussions, you know, with our team and with folks at the track, the guy that was driving the truck parked way too far away from the sample stand. And in order to get the sample of mix, we had to reach over the sample stand and like just barely get the shovel into the mix. We got a coarse segregated sample for that particular mix. So we we took some samples of that mix, melted them down, did ignitions, and we found out that that mix ended up being much coarser. Because the mix was coarser, that affected our trial mix weight. That actually changed the dynamics of what was happening. Because if the gradations are the same, you can just take a ratio of GMMs and you're fine. If the gradation's not the same, the mass to volume relation changes. So that's what happened here. Just as an addendum, the sections were fine. This was just a localized sampling issue that we had for one particular mix. And it was because the truck parked way too far away from the sample stand. One other thing I'll mention with regards to speed in production testing is there are some mixes that you just can't go fast with, particularly mixes with certain additives like rubbers or plastics in them. What you see here is a photograph of a sample that's been compacted, and we've got a 62 millimeter dowel bar in front of it. Now, the specimen was compacted to 62 mils, but for certain additives, it'll be compacted in the compactor and there'll be a rebound effect. It's almost like a spring being loaded. So you'll compact it, get it to 62, and as soon as you release the ram pressure, it's going to expand a little bit. Now, the way you mitigate this in the lab is through cooling the specimen in the mold, either still under a ram or with a weight on top, depending on the dynamics of your compactor. The problem with this is you can't go fast. So we actually had one mix at our test track with this particular issue. And the way we maintained speed was we actually used 3 gyratory compactors in parallel. We had samples in 3 gyratories at the same time under a fan, trying to get the specimens compacted as fast as we could so that they weren't sitting in the oven for an extended period. Now, is this something a normal lab is going to do? Is that an implementable thing? No, absolutely not. But it was something that we sort of did out of necessity for this one particular case. So just bear in mind, with BMD, when certain additives come into play, if there is a rebound effect, that's going to be something that doesn't allow you to really go fast. Okay, so that's kind of all I have, kind of summarizing our efforts for the 2024 track construction. I guess I will kick it to Joe, and then we'll take some questions at the end.
We began our journey, probably 8 years or more ago at West Contracting with looking at tests that go along with balanced mix design before we really even heard about balanced mix design. So today I want to talk to you about some of our steps. We'll look at the MoDOT's specifications. These are the most recent, not the ones that we've actually been operating under for some of our jobs in the past. Some of the challenges, and then some of the project data that we've collected. We began looking at the Cantabro test. We just did limited testing with that, and MoDOT didn't appear to be very interested in it. It wasn't widely accepted at that point. So we were getting a lot of hype about the iFit test. MoDOT said that they were looking at it. I'm not sure how much testing they did actually in their lab. I think contractors did more testing than they did for a while. But they also had University of Missouri at Columbia working on some of their test data. We just took our loading press. I put together a spreadsheet to evaluate it, and about the time we got to going good on it, MoDOT was showing that their interest in that test was kind of waning because of the CT index. We we got a new Instratech smart loader to help us with our evaluations, and and have been looking at different aspects of our mix and different mixes since that time. When the high temperature IDT came about, MoDOT wasn't showing much interest in that, and about the time that we knew about the RT index, MoDOT was kind of moving in that direction. So that and the Hamburg are what they ended up with as their test of choice. This is MoDOT's BMD specification. They allow the gyrations to be lowered depending on the level of traffic. The B traffic is the 30 to 100 million easels. C is 10 to 30, and then the lower traffic mixes are shown there also. Those don't come about too often. And this does go with their super paved designs. The air voids can be adjusted anywhere from 3 to 5%. The VMA is specified by a minimum VBE plus the design air voids. And or effective asphalt. Moisture susceptibility, they still use TSR of 80, but if you're not using a liquid anastrip, it's raised to 85. Cracking tolerance, they've set that at 50. They've got 135 for SMAs, but one thing that they want to look at is the critically aged, and so far they're just collecting information on that. The rutting RT index for a high traffic, they go by the graded binder that's specified for the high traffic, 80, 65 for the mid-level traffic, and 50 for the lower grades of asphalt. The Hamburg wheel track test, they've set that at 3/8 of an inch, and just for the design, they said that they didn't want to approve the mix at the limit of a 1/2 inch, and then have problems down the road. So they set their design minimum at 3/8. Their density, they've pushed it up a little bit. The minimum used to be 92, now it's 92.5 to 98. Asphalt content, they're still requiring volumetric testing along with the BMD. I'll talk about that a little bit later. Air voids within 1% of the JMF. CT index minimum of 135. And RT index, I think I've got the wrong. CT should be 50. RT index, the same as design, And then down here, there's a qualifier. If during production you don't meet the RT index, then you submit specimens for Hamburg wheel testing, and there your rut depth is a half an inch. And they also have a minimum allowable condition tensile strength of 60 psi tied to the TSR. They made their lots 6,000 is a maximum, sublots 1,500 is a maximum. So you can go lower than that. Say you want 750 ton sublots. Anyway, you can develop a sublot size that you're more comfortable with. So that'd be a minimum of 4 tests. You could have up to 8 tests that you may want to complete within that 6,000 tons. So for pay factors, they're looking at mat density of 1 sample per sublot, asphalt content. They're looking at 1 per sublot, and the air voids 1 per sublot. But then the CT index 1 every 3,000 tons. So if you had a 3,000 ton lot, it'd be once every lot. If it's a 6,000 ton lot, then it'd be twice per lot. And then they give you the number of samples you want. CT index will be run. You'll have 5 compacted specimens, but you throw out the high and the low and average the 3 in the middle. Then the RT index is just 3 compacted specimens. But one thing to note here is that every other test, the QA specimens will be made, and the QC people will make those under the supervision of the agency inspector. So, and then you also have your standard sampling for the volumetrics, and then a 250 pound sample for TSRs. Missouri uses percent within limits, and this is just an illustration of how that works. You take your lot, all the density readings in your lot, get an average standard deviation, and then use the table to determine your you determine your quality limits, and then a table will give you percent within limits. So if you can keep your the tails of this standard distribution curve within your spec, which would be 92.5 to 98, then you'll have 100% within limits. If you shift that average with the same standard deviation down, then you start to have material out of spec, statistically out of spec. So you could have densities that are all within spec, but then fall out of spec either by a wider standard deviation or by shifting too close to one end of your specification. Anyway, that's used to determine your pay factors, and they have 50% toward density, 25% for the air voids, and 25% for the asphalt content. For the performance test, the cracking test, CT index, can achieve up to 3% bonus if it's 100 or greater. If it's 50 to 99, 50 being the low end of your specification, you can get 100%. And then if it falls below that, between 40 and 49, 97%. And that's all dependent upon what your TSR value is. So if you want the bonus, you have to have 85% or greater on your TSR. Or if you use a liquid antistrip for full incentive, it's only 80%. Something else that they've done with this, looking at performance, is they included intelligent compaction and paver mounted thermal profiling in that also. I didn't want to get into that too much today. Some of the challenges that we've had, you got to look at your changes in your stockpile moisture segregation, the wrap binder content, moisture, of course, also the source and consistency. We take our wrap and crush it to a 3/8 minus, and really that keeps us a pretty consistent gradation. But something that can really throw us off is in the St. Louis area, there's a lot of rhyolite that's used as a friction material, and depending on how much of the rhyolite you end up in your wrap, it can really affect your properties. We had a job where our volumetrics all of a sudden fell flat, and then we discovered that unbeknownst to the technicians there at the plant, they had changed the source of it. And anyway, something that you constantly have to be aware of what's going on with your stockpiles. Your temperatures, you have to pay attention to changes in temperatures. Warm mix can help mitigate that, but it really it can affect the outcome of especially your cracking test greatly. Gradation and binder content, both as mentioned before, can affect your not only your test results, but also the specimen weights when you get ready to make those. When you're preparing your specimens, you really have to take, just like Adam said, you have to really take care with those truck samples. You want to make sure you get a good sample. You got to prevent roll down, so you're going to have to remove some of the material from the top of the truck and push it to the front or back, and so you don't have roll down of the coarser aggregates in the mix. And then splitting, same way. You got to have uniform splitting in order to take care of that. You really have to watch your time in the oven. MoDOT, due to some issues that came up, MoDOT has a hold at compaction temp for 30 minutes in the lab now. So that's additional time that it's going to take for all of your testing. We tend to compact at lower temperatures since you're compacting to a height and not really looking at number of gyrations. We've found that we can continue to compact our specimens at lower temps without really harming the integrity of your specimens. We found that loading molds with paper bags, we split out our specimens into paper bags to put them in the oven. That way, when we put them in, we're ensuring that we're putting it in a single mass rather than it just kind of trickling in off the edge of a bowl or something. That's really helped consistency for those smaller, thinner samples. And additives such as dry crumb rubber. We found that with a 9.5 millimeter mix and that has fairly fine gradation, you're going to get that rubber expansion or the rebound. And when we had a mix like that, it was over 2 hours between the start and completion of our compaction of the specimens. And then you have to make sure that when you store those, you have to have them plainly labeled, or because you're working with so many specimens, it really can get confusing, especially if the guy that marked them isn't the guy that tests them on the other end. And there's some of our compaction times. The time to compact 8 specimens in a big pine, we can do that in 20 minutes. In a baby pine, because of the way it extracts the specimen, it takes 40 minutes. And then GTR in a baby pine, because we had to weight our specimens down, is over 2 hours. To do it efficiently, we're finding that it takes at least 3 people at the plant, 2 to manage the plant and sampling, and 1 to manage the rock and stockpiles, keeping the moistures and looking for segregation, that kind of thing. Anyway, it really adds a lot into your time there, especially when you're still doing volumetric testing. Here's some of our project data. This is 3 different projects. You can see that 2 of the 3 projects had engineered probe rubber in them. Here's our design. This first one, we got a design, had a 160 for our CT index, went to production. It was 168, so we had pretty good results in trying to match those up. this was a 9.5 millimeter mix also. But you can see that some of the changes as the amount of number 8 changed in the mix, you can see some of the test results varied. This second job down there, the first one with engineered chrome rubber, it originally wasn't using balanced mix design criteria, but we were having trouble meeting our VMA and air voids, and I approached MoDOT and said, it's either remove asphalt, which would have taken 3/10 to meet our air voids, or use the balanced mix design. So they allowed us to reduce our gyrations, use the balanced mix design, and after we did that, the out on the roadway, the superintendent was able to remove one of the rollers out of the rolling pattern because they were getting density so much easier. And then one thing to note about the about the last job down here, it's 12.5 millimeter mix. We didn't have the trouble with we had a reduced amount of engineered chrome rubber in it, for one, but we also well, between the 12.5 millimeter and reduction in chrome rubber, we didn't have to weight those specimens in order to get our desired heights and air voids on our specimens. But down toward the bottom, the sublot 5 AC, that sample ended up with, I think it was 1.5% air voids. But when we tested it for CT index, it was a little bit higher than most of what we've been running. But also we had the Hamburg wheel testing performed on it and only had 6 millimeters of rutting, which for a very low air void was a very good number. That was one of the where they changed the source of the wrap on us. And I don't have.
Hey, Joe, we got about 5 minutes until 11, so I want to make sure that we have enough time for questions. If you could go ahead and
okay. Well, this is it. This is a job that we are still in the middle of, but the NCAT came and asked us if we could do our regular design, hot and warm, and then also do a balanced mix design, which is where it says has another design in there. That's our balanced mix design, and anyway, you can see that there's really not a whole lot of difference between hot and warm and between the two different mixtures. We did reheat some of the specimens and actually with the warm reheated, we still had better numbers than the hot mix did. Anyway, that was all I had. So,
Thank you, Joe. So just to kind of to wrap things up, and then we'll get to questions, recommendations. Some of the things I take away from Adam and Joe's content is, one, sample more material than you need. Right, you're going to need to blend it together and homogenize it. One of the things that Adam touched on is make more samples than you think you'll need, and I think Joe talked about that as well. Identify opportunities for efficiency. That's something that both speakers sort of touched on. And efficiency doesn't necessarily have to mean sacrificing quality. So find those opportunities and exploit them. Pay close attention to specifications and potential specification changes. Joe, you had a lot of information about some of MoDOT specs, and making sure that you're staying up to date on what the state is requiring or looking at, and then what's changing. That's really important. I think the main takeaway I got from Joe's talk, and then also bits of Adam's, is consistency is extremely important. And in Joe's case, especially if you're in a PWL specification, I mean, that's the name of the game. It's all about being consistent. And one of the things I love that you talked about it, Joe, is monitor the time in the oven, and that it is okay to compact at temps that are lower than the compaction temperature. That's something that I know Adam didn't talk about, but that's something that we do as well. You can make really good samples at 270 degrees or even lower, depending on some material. So with that, I'd like to open it up for some questions. I'm going to stop sharing my screen in a moment, but here is the contact information for the presenters today. Myself's on the top, and then that's Adam and Joe's contact information as well. The first question is, what are your thoughts around the ideal RT versus the high temp IDT or the Hamburg test?
Okay, so this was sort of our main impetus in the production testing for the 2021 track. We essentially were doing a similar exercise, but we were testing high temp IDT side by side with ideal RT. And for the mixes we had 14 mixes, again, wide range of materials, different states, different designs. We saw a very strong correlation between the two, between the high temp IDT and the ideal RT. I don't know if that's enough information to say it's like universal, but with our data, those two correlated very well. Our takeaway was to pick one. We were going to either run the high temp IDT or the ideal RT going forward. We weren't going to continue to run both tests in parallel. We made the decision to conduct the high temp IDT in conjunction with the 2024 test track, because that seems to be the direction. Well, it's definitely the direction ALDOT has gone, and along with some of the other local state agencies. The high temp IDT is not an ASTM spec yet. It is, I believe, a draft spec that is moving through the ASTM process. The ideal RT is an ASTM spec. I believe it is D8360, if I remember correctly.
yes, we haven't run enough of it to really see, what the difference is in the two, but they move together in what testing we've done. And of course, we do the ideal RT because that's MoDOT spec, but also I think that is a draft AASHTO spec now also.
Could you guys speak to the how those two tests compare to the Hamburg?
What we saw in the 2021 cycle, we ran Hamburg. We looked at Hamburg. We looked at APA. The results of that small evaluation were published in an NCAT newsletter article, I believe, spring of last year or the year before. Essentially, we saw a pretty good relationship between the rapid rut tests and the Hamburg. We didn't see as good of a relationship between the APA and the rapid rutting tests, but since then I've seen some other data sets where there is a good relationship between the APA and the rapid rutting tests. There's exceptions to every rule. The most notable exception in my mind is gap graded mixes, SMAs or OGFCs. Those mixes tend to perform really poorly in terms of indirect tension peak load. They're going to have very low indirect tension peak load, hence they're going to have very low HT-IDTs or RT index, but generally speaking, they're going to perform well in the Hamburg. We had a mix like that just on this previous test track. It had an HT-IDT, it was an SMA, it had an HT-IDT of like 12 or 13, but the Hamburg was fine. It was like 5 or 6 mils at 20,000 passes. So that's your notable exception to that rule. Otherwise, they tend to relate reasonably well, in my opinion.
And I know, Adam, I know you and some other researchers at NCAT, y'all are working on compiling all of this for a potential NCAT report, putting all that stuff together. Shane Buchanan actually he just put something in the chat, some figures that Adam actually made on a report that we did for CRH, kind of just giving data to back up what Adam just said related to those relationships. So, that's one more question. And Tanya Nash had a question. You guys kind of touched on it, but any other comments though on correlations between some of those routing tests, APA and Hamburg and ideal RT and high temp IDT? Anything you hadn't touched on?
No, that's just one thing that, like Adam said, SMAs are a little bit different animal, and so you have to make some pretty good adjustments in order to properly evaluate those, because they are going to be much lower than a dense graded mix.
So, Joe, I'm gonna point this next question to you, and Adam, chime in if you've got comments. But Jeff Anderson asks, when compacting at lower temperatures in the lab for production, would you also would you do lower temperature compaction when developing the initial lab design as well?
We do not do that. But one thing that we do in the lab that we think helps us match our field numbers a little bit better is we do age those for 6 hours or 4 hours instead of just the 2 that's required currently for short-term aging.
Okay.
Yeah, we typically do not as well. For laboratory design, again, for this test track, we're doing mixed designs from several different states. Some of them follow the old R30, which is the 4 hours at 135C. Some follow the current iteration of R30, which is 2 hours at 135C. So we were essentially following state guidance on laboratory aging. I didn't really dive down on it in my presentation, but we also don't really try to get specimens up to compaction temperature for production testing. As long as they are sufficiently hot, they're going to get to a height in the gyratory compactor, unless there's something weird in there, like a stiffening agent of some kind. In that case, you do need temperature. Sometimes for rubber mixes, that does require extra time. But as long as you're getting to a height and a reasonable number of gyrations and you're not breaking stone, for production testing, our rule is just go as fast as you can because that mix has already been through a plant.
Well, I'll add a quick question, and then we've got one more about engineered chrome rubber. What's a typical number of gyrations it takes to reach height at these lower temperatures?
It varies. Again, we had, it's a completely random pile of mixes for this 2024 test track. We had some mixes, I would say the average is in the 20s, somewhere around there. We had one mix compacting to a height in 7 gyrations, and we had one mix taking about 80. And that was, that one kind of slowed us down a good bit. So it is mix dependent, but on average 20 to 30.
So one more question. This is from Tom Knotzman. How are the engineered chrome rubber mixes performing with the ideal CT and the ideal RT?
They do pretty well. I do think that the RT maybe runs a little bit lower than it would if you didn't have the crumb rubber in there. Crumb rubber is one of those anomalies that it really gives you good rutting resistance, but it's hard to show that in the test sometimes.
So we have one more question come in, and we'll close out with this one. And Tanya Nash with a really good food for thought question. So Adam, I'm going to kick this one to you. So Adam, you hinted that the peak strength can give you an idea of how the RT and the high temp IDT will turn out. I mean, it's certainly the case as part of the equation. But is there a way that you could just use the the peak of the CT index tests instead of another test to evaluate rutting?
This is one of those things I've only ever taken a quick look at and not really chased all the way down the rabbit hole. The HT and the RT, the index or the strength is calculated from the peak load, but that peak load is tested at 50C. For CT, the peak load is from 25C. So, you do have viscoelastic time temperature superposition effects come into play. So it's not exactly one-to-one depending on the material. I took a quick look at it in 2021 and didn't see anything, but I have new data now and it bears circling back to. I just haven't done it yet.
Yeah, I agree. All right. Well, I want to thank everybody for coming out. I'm going to switch back over here really quick. Thank you everyone for attending. As always, if there's more information on our website, so ncat.us, and so you can have access to all of our test track reports. Travis does a great job with the training in your pocket content on YouTube for just sort of quick summaries on test methods or ideas, and they also have a little bit of asphalt nerd humor in them, so that's a great resource. NCAT offers training courses related to lots of these things. Adam actually teaches a whole entire session on specimen preparation for balanced mix design, and we touch on production in there. So feel free to check out the training resources on the NCAT website, and go ahead and save the date for February 20th. Same time as always, third Thursday of the month. We're going to be talking about mix design tips for recycled and alternative / non-standard materials. So many of us are familiar with doing mix design with wrap, but what about with additives or with maybe non-natural aggregates like slag or lightweight aggregates, things like that. So it should be really good. Graham Hurley is going to be our NCAT rep, and we're excited to have that. So we will see all of you guys hopefully in a month, and enjoy the rest of your day.